Right, hi everybody. I know this is not an ideal way to have a problem class, but me, Jeff, and Giuseppe had a little chat. I thought at least this would be a way to talk you through the problems and hopefully give you kind of at least a reasoned way of answering the questions. Given that obviously you can't ask questions during the video, if you do have any, please send me or Jeff an email and then we can sort it out from there. So that's james.alvey and then @kcl.ac.uk. Obviously, these are quite unusual times, so we're just trying to make something work. Anyway, let's get into it so this video isn't too long. Talk about question 1, in particular the first part. So we'll just talk about the setup, we'll talk about what the different quantities mean, and then try and build a bit of intuition. And then later on in the question, we're going to say, okay, what does this mean for this notion of cross-section? How does it compare to what we call a geometrical cross-section? And as usual, kind of what happens if we put some actual numbers in. Right, so if we look at the diagram on the left-hand side, what we're going to see is a planet A of mass little m and a big planet B of mass big M. So the whole point of this setup is trying to understand what happens if a big planet has a little planet flying by it. Now, if there's no gravitational interaction between those two planets, as long as the planet A was moving sufficiently far away, i.e. bigger than the radius of the planet R0, from planet B, then nothing would happen. The planets would just go straight past each other. The point is that when there is gravity, you get this additional attraction, and if it passes a distance, we're going to call it B, we're going to try and find out some information about B. But if it passes slightly further away, there's still a possibility that A crashes into B. And that's, again, simply due to the fact that there's an attraction between the two planets. So it says in the question on the problem sheet, but just for simplicity, we're going to model A just as a point mass, but we're going to give B some structure. So it's going to mean something that has some radius R0. So the first part is about, okay, how do I relate some of these quantities? We're going to use conservation of energy. We're going to use conservation of energy for A, in particular in the rest frame of B. So there's a couple of quantities to look at here. Firstly, there's this VRAN. You can think of this as the kind of random motion of stars in the galaxy. We'll come to that a little bit later on when we start to think about the Milky Way. You've got Vmax, and this kind of, if you think about it in energetic terms, this has to be the point at which planet A hits planet B, just because that's the point of lowest potential energy. And there's also going to be an escape velocity, which you've calculated loads and loads of times, and it's given by kind of the square root of 2g times big M over R0. So if we want to put those together, initially, we're going to work in the rest frame of B. So the potential energy initially, if A is really, really far away, is 0, and the kinetic energy is just a half times little m times VRAN squared. When the two actually collide, so this is when the maximum velocity is obtained, the final kinetic energy has to be a half times little m times Vmax squared, and the potential energy is just the Newtonian potential energy, which is minus G capital M little m over R0. So if we set those two equal to each other, i.e. the total initial energy, Ki plus capital Ui, and the total final energy, so Kf plus Uf, then you get the expression that's shown just near the bottom, which is a half m VRAN squared, is a half m Vmax squared minus GMM over R0. So if we do a little bit of rearranging, then we just find we can cancel some of the little m's, and we find that VRAN squared is Vmax squared minus 2GM over R0. And then we play this game of, okay, I recognize that last part of that expression. Unfortunately, we're trying to do a kind of show that, so we know where we're going with this. But we recognize that last part as the escape velocity of the planet B squared. So if you put that in, then you find the boxed result, which is what's on the problem sheet, which is that VRAN squared is Vmax squared minus V escape squared. Okay, we're going to have a look at part B now. So part B, we mentioned that impact parameter B. So the impact parameter is kind of what's the furthest point of approach that I can still have a collision between A and the star B. So again, to approach this problem, we're going to conserve angular momentum of A about B. So what does that mean? Well, let's look initially. Initially, I have some linear momentum m times v ran. And then the angular momentum of that about B is the momentum times the perpendicular distance. But that's just a definition of the impact parameter B. So this initial angular momentum, Li, is equal to mv ran, which is the linear momentum, times B. We can do the same thing at the final position, and we find that the final angular momentum of A about B is m times v max, again the linear momentum, times r naught. Now, there's no torque on A. To understand why that's the case, you just have to think about the fact that gravity is acting as a central force here. So the force only acts between the center of B and A. There's no torque on the motion, and that means that the total angular momentum of A has to be conserved about B, and that means that we can set Li equal to Lf, and then we can relate B to something that we know, which is r naught and the velocities. So that gives you the expression that v ran times B is v max times r naught, and if you want to rearrange that for B, you can find that B is v max over v ran times r naught. So what do we actually want to calculate in this question? What we really want to calculate is the cross-section. So the cross-section is a type of area. It gives you an idea of, if I'm a planet A, a little planet A, again, we'll think of it as a point mass for now. If I'm a small planet A and I'm approaching this bigger star B, what do I see? Like, how big does B look? When I say how big, I mean how likely I am to collide with that star. So again, you can, if you think of what B looks like when I go head on, it looks like a big circle. So it has some area that looks like pi times some length squared. In particular, it's pi times the impact parameter squared. So to actually calculate this, at least how it relates to the geometrical cross-section, the geometrical cross-section is literally, what does B look like? Well, it is a circle and it has area pi times r naught squared, the actual radius of the star squared. So if we take the ratio of those two, sigma over sigma geo, we find that that's pi b squared over pi on r naught squared. We haven't done anything there, that's just the definition of both of those quantities. And now I'm going to use the physics. So I now need to know something about the system, and importantly, I want to know something about B. So if I plug in my expression for B that you find by setting Li equal to Lf, then I find that sigma over sigma geo, I take the pi's cancel and I get a 1 over r naught squared from the denominator. And then I get another factor of r naught squared from the B, and this additional factor of v max squared over v ran squared. So if you note here that the two r naught squareds cancel, and I find that sigma over sigma geo is just v max squared over v ran squared. We're almost done. We've almost got the result, but we just need to go back and remember how we relate v max to v ran and v escape, and then that's just the result from part A if I add v escape to the left-hand side. So if I do that, I find that sigma over sigma geo is v ran squared plus v escape squared all over v ran squared. You can, take v ran squared out, and then you find that sigma is in fact sigma geo all into 1 plus v escape squared over v ran squared, as you need. So in the final part of the question, part C, we're going to say, okay, we've got an expression for this cross-section. We've got an expression for how big does B look when I include gravitational interactions. You expect that this answer, well, by definition, it has to be larger because I'm multiplying by a factor that's bigger than 1. The question is how much bigger. So let's take some typical values. In particular, we're taking an escape velocity of about 620 kilometers per second. And if we take a random kind of stochastic motion in the galaxy of about 20 kilometers per second, if we plug them in, we find that the ratio between sigma and sigma geo is 1 plus 620 over 20 all squared, and that gives you about 962. So this is not an insignificant effect. This is the point of plugging these numbers, and again, why I emphasize a lot when I teach these classes, it's really good to get a feel for these numbers. What does it mean? Well, actually, it says that when I include gravitational interactions, these kind of stars or big gravitational objects look much bigger to oncoming kind of particles or masses. And this is important because actually a lot of galaxy formation is driven by collision. I need collision between objects in order to generate more structure. So this is an important number. So if we move on to the second question in the problem sheet now. So this is the Jupiter notebook. It's on the Keats page. You can go and access it. And I'd also recommend that you go and look at a picture of the Milky Way. So the whole point of this question is, okay, I see spiral galaxies in the universe. In particular, the Milky Way is a spiral galaxy. And we want to understand, can we come up with a good formation mechanism for these spiral arms? We're going to try a very simple model in the Jupiter notebook, and again, it's partly to get some idea of the astrophysics. It's also to get some, an idea of some good programming tactics and some good plotting. We're going to try and see if just following and tracking stars going around the center of a galaxy over kind of order gigayears of galaxy evolution, if we just track those and count how many times they go round the galaxy for typical values of the speeds, can I explain the spiral pattern that I observe? And the thing that we're going to compare to is, of course, the Milky Way, and you're going to note that the spiral arms, they wrap all the way around the galaxy, but they only wrap around once. So if we write our code and we run it and we find arms that go round once, maybe we found a good mechanism. If not, we need to come up with a new idea and see where we're at. So we're going to talk through the Jupiter notebook very quickly. So I'm going to start, just do the imports, of course. Then we're going to define some functions. So in this case, we're going to define the theta function. We're going to say, okay, if I start with some theta naught, how do I get to the next one? And that's really just theta naught plus omega times t. And then we're going to say, okay, once I have an angle, how do I get x and y? And that's just kind of the radius times cos of the angle, or the radius times sine of the angle. So just some normal kind of converting from polar to Cartesian coordinates for when I want to plot. And then I'm going to set it up. So I'm going to set up just some initial grid. As it says, we're going to make the arms at t equals 0 along the x-axis and just point them outwards, and then I'm going to spin them round. And I'm going to spin them round with minus 220 kilometers per second. That's the velocity. Note that it's negative because we want to go clockwise, and I'm going to run it for a very long time. I'm going to run it for a gigayear. So the last part is, okay, I do my running and I plot my result. What do I see? Well, importantly, I see arms that have wrapped round many more times than you might expect. So just to conclude then, what can we take from this? Well, we can take that the formation mechanism of the arms is not the stars themselves going around the center of the galaxy many times. This gives kind of a spiral pattern with far too many features compared to the Milky Way, which really just has one over kind of order gigayear timescales. So what's the actual explanation? Well, there's a notion perhaps of a more collective effect, a more kind of, it's not individual stars that move, but it's groups of stars that move, and they move with a slower kind of bulk velocity, kind of a stellar wind. And that's the general idea of how I can have motion around the galaxy of stars, but not have too many rotations. So again, just to end up the problem class, I hope this is at least a reasonable alternative, and it will be the case, I imagine, for the foreseeable future, how these are set up, unless we can set up some form of live setup. But again, if there was something that could be done better, I'm very much happy to try and include that. If people would like, again, more explanation on a given point that I might have rushed through, again, just let me or Jeff know, and we can organise something. Anyway, thank you very much.